is advancing. Cool. Hello, y'all. All right, so this is actually not the title of my talk, but I thought this is more important than the title of my talk because I am actually going to give away starbursts because I want this to be a little bit more interactive. So if I have questions, just raise your hand, and then I'm going to try, if you get the right answer, I'm going to try and get my best aim to give it to you. So it might be a little hard for those at the top. So I'm going to just give you guys brownie points when you guys do answer it correctly. And so since none of the trivia questions are coming from my talk, I figured out I should probably give you guys trivia questions as well. And so if you have the sheet, we're going to have a quiz that's worth 5 points. So you can write on the back of the sheet, and you'll have like 10 seconds to answer them. No, I'm kidding. So my first question is, what are the ingredients in making a galaxy? Who said that? Sure, yeah. That was really bad. Okay, any other answers? Raise your hand, please. Come on. He said hydrogen, which is like basically all of the universe. So I should, yeah, so he deserves the starburst. Yes. Okay, cool. All right, I'm going to give that to you too. I'm looking for more like bigger things than those. Yes. Black hole. Okay, I'm going to just give one of the answers right. Stellar material. Sure. Oh, that's really bad too. All right, you over there. What? Vacuum. You know what? I'm just gonna give the answers because I'm gonna run out of the starbursts on the first slide. Gravity is one of the most important things. Stars, dust, gas, ET, dark matter. Right. Okay. So we're gonna go back to that later. And then give me just like 2 kinds of galaxies over there. Spiral and elliptical. Oh man, so you deserve 2. Okay, cool. I tried. Okay. I'm going to run out of these starbursts soon anyway, so yeah. So ellipticals and spirals. So the actual title of my talk is actually about how different stars and effect on stars make different galaxies. And this is basically my research for my first and second year. And also, I'm going to say bamboozle a lot. I like that. So every time I say bamboozle, you got to go drink if you want to be really drunk and turned up at the end of my talk. All right. So just to recap, y'all really failed this quiz a while ago. So we got to get over that again. So you have a frying pan, put it on the stove. Just a recap of galaxy formation, right? So you have stars, you have dust, you got gas, and you have something that we don't really freaking know, and so it's just a big question mark. But we call it dark matter, and it makes up a lot of our galaxy. And so you put it on the frying pan, definitely for more than 10 minutes. Probably hundreds of thousands of years or millions of years, billions of years, et voila. You got your galaxy. And that's the end of my talk. Thank you. No. All right. So here you have a spiral galaxy, and as I said a while ago, it's made up of a lot of different stuff, but the main things are stars, gas, dust, dark matter, and they're all binded together by gravity. But for my talk, I'm just going to talk about the bright stuff, which are the stars. Good. Okay. I was actually telling Will a while ago that he basically covered half of my talk, so this should go really fast. So as you see here, can someone describe to me what this field of stars look like? What different kinds of stars you can see? Raise your hand. Who? Someone said something there. Yes. Blue stars. And the other one, yes. Red stars. Cool, yeah. So we have blue stars, we have red stars, and we have the rest of the colors in between. That was really good. Good job. Um, and so these colors usually point to the temperature of these stars. So blue stars are hotter, red stars are cooler. But sometimes these colors are actually affected by other things, and so the colors can actually bamboozle you. Hey. And it actually could not be a matter of like the temperature. And so this makes figuring out what stars make up a galaxy very, very, very hard. And so that's my research, and that's why it's taking me 2.5 years to do this paper. But it's important to characterize these. So you've seen this one a while ago. So there's going to be 3 bamboozlements. And the first bamboozlement is something to do with the age of stars. So are they young or old? So you guys have seen this a while ago with Will's talk. It's the HR diagram. And I wanted to make the joke that we astronomers don't know how to put axes because temperature goes the wrong way. But I can't say it anymore because it's not new. But at least luminosity does go up. As luminosity goes up as you go up the vertical axis. And so I just want to focus more on the main sequence of stars that goes from the top left to the bottom right. And these stars are very important because most stars actually live while they're on the main sequence, and this is when they burn hydrogen. And so bluer stars are the more massive stars. Redder stars are less massive and they're cooler. And all these stars actually live by the saying, live fast, die young. And when I Googled this quote, I didn't know there's a second half to the saying, which is have a good-looking corpse. But good-looking corpses they do have. So for high-mass stars, you got, they can turn into black holes. That's actually an artist rendition. But that would be cool if we could actually see black holes. And then the stuff that Brian studies, some of the higher mass stars, they end up into, collapsing and being supernova. And you got this beautiful supernova remnant with like a neutron star in the middle. And then for stars like the sun, they end up like white dwarfs. And you have the planetary nebula surrounding it. And so, right, live fast, die young. Right? So what happens is the bluer, hotter, and more massive stars die first, and then followed by the less massive ones, let's say the yellow stars. And in the end, if you have a group of stars in the field, most of what's actually going to be there is just the cooler M dwarfs, the red stars. And so how this is going to look like when you look at a spectra, does anyone know what shape this is? No. Good job on guessing, though. I like that. I don't know who that was, but here's a starburst. Yes. Blackbody. Woo. All right, so stars emit... Yo, this is why I'm not in the softball team. Yeah, I'm like backup of the backup. Yeah. So stars emit blackbody radiation, and bluer stars emit and peak at bluer wavelengths. So the brightness goes up that way, and color goes from blue to red, from left to right. So when those blue stars die, those most massive stars die, you don't really see the light from them anymore. And so the peak shifts to redder wavelengths, and also the luminosity drops. So then, for an older population, you might actually just see, just more of the yellow stars. And then for even older populations, these yellow stars may have already died too. And so the luminosity even further shifts down, and the peak further shifts to the red, and you're just left with the red spectra of the stars. And so that's bamboozlement number 1. So that's age. And we're going to move on to bamboozlement number 2, which is something to do with the metal content. So you guys may have seen this famous turtleneck dude from the first talk. Yeah. So he has this famous saying wherein, if you wish to make an apple pie from scratch, you must first invent the universe. So I'm actually going to step on people's toes here and say that's not completely correct. Because when the universe was first created, most of it was hydrogen. And then the next one that it's made up of is helium, and there's some trace elements of lithium and whatever. And the rest of it we call metals because we're astronomers. And an apple pie is made of metals. But these metals are not born when the universe was created. They have to be created inside the stars. And so the stars, they born hydrogen in their core, and then helium, and then carbon, and yada, 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 until you get to iron, right? And then all these at the end of the star's life gets dispersed out into the interstellar medium. And so next generation of stars can then use these metals as part of, the new generation of stars. So the more star formation events that you have, the more metals there are going to be. So again, for higher mass stars, they can end up being, oh no, where's the light? There you go. They can end up being, supernovas, or they end up as white dwarfs for the planetary nebulae. And everything that was made inside the star is spilled out. All the guts spilled out into the space around it. And so what happens is when we have more metals, there's going to be a lot more of transitions for the electrons. And when there's more transitions, there's going to be more absorption in the continuum. And so if you have a lower metallicity star, it could be like blue looking like this. Oops, blue over here, and not many, no absorption features at all. That's mainly because I was too lazy to put on the lines. But for higher metallicity stars, there's a lot more of transitions that these electrons can make and more absorption features. And so it eats up the continuum, and then you have these dips over here. And that's what we call metal line blanketing. And so high metallicity stars are actually redder, and low metallicity stars are bluer. So that's bamboozlement number 2 that can bamboozle you. So that's 2. Bamboozle you, about the color of the star that you see. So bamboozlement number 3 is some of our grad students and other professors and postdocs' favorite, which is dust. Question mark, question mark, question mark. So this patch over here is not just an empty patch of the sky with no stars in them at all. Because when you look at a different wavelength, so this is in the optical, if you look at the infrared, there's actually stars behind it that's just being blocked by this patch of weird looking thing, which is dust. So what dust does is, so you have the starlight over here, and then when the light of the star goes through the screen of dust, the dust absorbs this optical light, and it preferentially absorbs the bluer light than the redder light. And it also scatters it. So all that you can see is the redder wavelengths that's not as scattered and absorbed as the blue light. And that's why in the previous picture, when we look at the redder wavelengths in the infrared, we can actually see through, because all these stars, they're blackbody radiation, and they actually emit in all those different wavelengths. It's a matter of where they peak when you actually see them the best. So no, this way. Cool. So then what happens is dust absorbs the light on the bluer side preferentially. It absorbs in the optical, and then is re-radiated in the far infrared. So that's bamboozlement number 3. And all of these 3 things, age, metallicity, and dust, they form this degeneracy because all of them basically turn your star into something that's redder. It's probably not just because of the temperature. And so as someone who studies this and gets paid as a grad student, to do this research, I have to be very, 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 very careful about figuring out which effect is actually making my star red. And this makes dealing with colors harder, because if you just have color that's red, it could be any of these 3 effects. And so instead of just having colors and photometry, I have the privilege of actually using spectra because that has a lot more information. And if you have the full spectra, you actually can disentangle the different effects of age, metallicity, and dust. And so that's where the data that I'm using comes into rescue. So it's integral field spectroscopy. And what that means is that for every point over here, for every circle on this galaxy, there's actually fiber optic connected to that. And all of the light over here actually gets dispersed. So compared to having long slit spectroscopy, where you just have like, one slit and then the integrated light for that galaxy, you have spatially resolved information for this galaxy, which is this over here, this image here. So you have the 2D image of the galaxy, and then you have a third dimension, which is the flux, the intensity of the galaxy in all of these different wavelengths. So having three-dimensional information in X and Y space and also in spectral space makes it easy for us to, well, not easy, it's still pretty freaking hard, makes it a lot better to just disentangle the effects of age, metallicity, and dust on every part of a galaxy for different types of galaxies. And so for my research, I actually use data from this cool observatory, which is, if someone can tell me, it's actually on the... Oh, McDonald, yeah. Who was that? Okay, I'll give it to you later. Yeah. So it's the McDonald Observatory. Yes, so for this data, we actually use the 2.7 meter telescope. And I use data from the survey called Virus-Speed Exploration of Nearby Galaxies, or VENGA. And there are IFU pointings at 30 nearby galaxies taken at the McDonald Observatory for 150 nights, which I did not take. So it was someone else, and I'm reaping the benefits of their hard labor. So I'm really thankful that they did that. And then what I do with that data is I do stellar population synthesis, which is basically combining all of the effects of these three bamboozlements into a code to figure out how much each of them contribute to my spectra at every part of a galaxy for different types of galaxies. And this is actually pioneered by someone who's a UT alumna. This is Beatrice Tinsley. And yeah, she actually has, yeah, let's clap for her. Yeah. She actually has a New York Times article. Well, there's an article about her in New York Times in the Overlooked No More. So I suggest that you guys look at that. And one of my ultimate goals is to figure out which office she used while she was a grad student at UT. So if any of you guys know, let me know. Yeah, and so she pioneered this field that I'm doing, stellar population synthesis, wherein when you look at the integrated light of a galaxy, you can basically figure out, the star formation history, how it's evolved, the ages of stars, metal content, dust content, by disentangling the types of stars, like the different spectra that each different types of stars contribute to it. So that's what she did, and that is what I'm doing as well for my research. So I use this galaxy, NGC 2903, from the VENGA survey, and basically I'm gonna give like a 2-sentence summary of what I did for 2.5 years. So basically what I found for this galaxy is that for the bulge region of this galaxy, there's higher metal content, so there's been a lot more of star formation events that happen there, and there are older stars. And as you go towards the outskirts of your galaxy, you have younger and younger stars and also lower metallicity content. Also, there's higher star formation on the spiral arms. And then, in contrast, other people have also used stellar population synthesis for elliptical galaxies, where they find that elliptical galaxies are basically higher in metallicity, older, composed of older stars, and they also are higher in these elements called alpha elements. And these alpha elements are traces of rapid star formation. So that's not the same. We don't find as much of these alpha elements in spiral galaxies. And so just by doing stellar population synthesis, knowing the age, metallicity, and dust content of these galaxies, we can backtrack how they actually formed. And so that's the end of my talk. And I just want to end here with a poem that I wrote for 2 minutes. And it's called Do Not Be Fooled by How a Star Appears. Old stars are red. Young stars are blue. High metal, red. Low metal, blue. Dusty is red. No dust is not going to change the star. I couldn't rhyme that. Don't let stars' colors bamboozle you. Thank you. Questions?
All right, let's take a few questions. Let's start over there.
There are green spectra stars, so it's a matter of just me being lazy to put all of the the black bodies. But if the sun is actually kind of like a green star, so it peaks at greener wavelengths. But since we see it's very near us and we see all of the light that's coming from the sun, it's basically just white light. So there are stars that peak at green wavelengths. Yes.
All right, there was someone right next to him. Do you want to ask a question as well? Yes.
Oh, cool. I'm sorry.
All
There
right.
are green stars.
All right, balcony. No, all right, how about right here?
How much does redshifting and blue shifting from movement affect the color versus the other effects?
That's actually a pretty good question. So I don't know if everyone heard, but how does red shifting and blue shifting affect what we see? So that's one of the first things that I actually account for in my research is how much the velocity affects the spectra. And then once we got that figured out, and so for example, for spiral galaxies, we know that there will at least be like a rotation, signal of rotation. So one side will be red shifted, one side will be blue shifted. And once we take that out of, we take that into account, then we actually fit the stellar populations. Yeah.
All right, how about right over there?
Yeah. Oh, man. Okay. Yes. Yeah. Mm-hmm.
Which is a more big effect on putting stuff out there? Don't bamboozle me.
Yeah, okay. So I'm not an expert on supernovae and kilonovae frequencies, but I would think that kilonovae, since they're a lot more energetic, that it will actually create different types of elements. Because so past iron, we can still form higher elements, but it's a matter of neutron capture. So it depends on the density of neutrons. So I guess that's also gonna depend on how energetic the event is. So I'm assuming for a kilonova, the electrons will be going way faster. So I don't know if neutron capture will be easier or harder for that. Probably harder. But yeah, I would think they will make different elements.
All right, how about right up here?
Does dust ever polarize or cause a refraction like coming from the stars, and could that skew the apparent size of stars?
That's a good question. So the question is, does dust ever polarize the light such that it affects the size, the apparent size of stars? I actually do not know the answer to that. Is there any dust expert here? Yes. Does dust affect the apparent size of stars? No. Yeah. Yeah. Okay. Yeah. Yeah, I had to outsource that because I'm not an expert in that.
All right, maybe one more question if there is another one. There we go in the back.
It's from ModCloth. Yeah. It's pretty cool. I like it.
And with that, let us thank Dreia again.